In this video, we'll be talking about volume and composition of combustion products. Again, we can look at the relationship CXHY plus X plus Y over 4 O2 that combusts and leads to CO2 and water. So for every, and there is here like a correction, this is an X, not a C. So for every mole of CXHY that we can see over here, it reacts with the air. They go inside the combustion chamber, which is this one. The reaction happens and they come up with X mole of CO2, Y over 2 moles of H2O from the combustion. There are other things that we really need to think about. There is dry and total N. So what are the dry and total N? Just take a second to think about that. So usually when we are having air that comes in, this air will have humidity of some sort. If the humidity is 0, then we are only talking about oxygen and nitrogen. However, if the humidity is high, we are adding another complexity into our combustion. So the N dry just refers to dry gas, dry air without any humidity. So N total is equal to N dry times 1 plus X, where X is the humidity expressed as mole of H2O per mole of dry air. On the other hand, N dry is equal to N stoichiometry times 1 plus E over 0.21, where E is the fraction of excess air introduced to the burner. And excess air is important because if we don't have excess air, we'll be operating at limited oxygen under the optimum. So we usually add a little bit more air also for losses. So we have an E. Out of this comes Xn dry air, mole of H2O from air, and 0.79 N dry air mole of nitrogen from air, En stoichiometry mole of oxygen, that's the excess oxygen that comes out that did not react, and the total mole out will be of oxygen will be X plus Y over 2 plus N stoichiometry 1 plus E over 0.21 times 1 plus X minus 1. This is the total moles that come out. Let's try to see this in an example. In this example, we're saying methane is burned in air with 20% excess air and air moisture of 0.0116 mole per mole of dry air. What are the flow rates of combustion air and the composition and flow rate of combustion products? So here we choose our basis as 1 mole of methane so that we can calculate the flows per mole of methane. E is equal to 0.2 and X is equal to 0.0116. Let's look back here. E is equal to 0.2 and X is equal to 0.116. And assuming 1 mole, we can really calculate what is N dry, we can calculate N total, we can calculate how much CO2, how much H2O. So if we really know this too, and we know what we are burning, we can, if we assume 1 mole and we know the E, we know the X, we can directly calculate the N dry, N total, and then CO2, H2O, nitrogen, excess O2, total moles going out. Similarly, here we'll have the N CO2 is equal to X is equal to 1. N of H2O, combustion, Y over 2 is equal to 2. N stoichiometry, X plus Y over 4, which is 2. N dry, N stoichiometry, 1 plus E over 0.21. So this will be 11.43. N total is N dry 1 plus X, 11.56. N2 will be 0.79. N dry, 9.03. NO2 will be 0.4. And then the NH2O total is equal to NH2O combustion plus XN dry, which is 2.13, and the total N out is equal to 1 plus 4 over 2 plus 2 times 1 plus 0.2 over 0.21 times 1 plus 0.0116 minus 1, which is 12.56. So based on this, on the givens here, the values and composition of combustion product, we can actually know every part what's coming in and what's coming out, including the humidity in the air. So a typical Pittsburgh steam coal has ultimate analysis by weight: hydrogen 5%, carbon 75.8%, nitrogen, sulfur, oxygen, ash. It is burnt with 20% excess air with humidity of 0.0116 mole per mole of dry air, and combustion is complete. Determine the amount of composition of the gas produced. So I will leave this one for you. It is solved actually in the slide. So you can actually try to do it by yourself and try to look at the answers for this one. Next and final in the combustion chapter, we'll be talking about volumetric flow rates. Volumetric volumes change significantly with changes in temperature and or chemical composition, just like how we were talking about in a minute, where we talked about P1 V1 over T1 is equal to P2 V2 over T2. The changes complicate the design of all types of air pollution control equipment. So we usually look at molar flow rate rather than volumetric flow rate, because the amount of moles that is available is constant, while the amount of volume available changes, since gas is compressible fluid, different than water. So the molar flow rate is equal to mass flow rate over molecular weight. So for example, 100 pounds per minute over 29 pounds per pound mole. And we can use this to convert between actual flow rate and standard flow rate. Again, the main equation is P1 V1 over T1 is equal to P2 V2 over T2, but you can use any variation of it similar to what you have here in this slide. Thank you for listening to this chapter, and good luck in your course.